So welcome to Rajashekhar classes on applied data science with Python. This is lecture number 593. In this lecture, I will continue my discussion on CPUs versus GPU. Let's go to GPU. GPU has a different architecture. You have first, I request you to go through my previous lecture before understanding this lecture. In the case of GPU, you have your RAM, isn't it? Just like in the case of CPU. Even in the, just try to recall my previous lecture where we discussed about CPU. Even in the case of CPU also you have RAM, isn't it? But the structure here is very different. The structure here is in the case of CPU. What is the structure? You have a computational computational structure, and RAM. Just see, this is the computational structure. This is known as RAM. This what is this RAM? This is memory unit. I can say RAM can be treated as memory unit. So on a single chip, or you have cache, and these cores, first core, second core, third core, fourth core, all of them are on single chip. This is about CPU. In the case of GPU, you may have single chip or small set of chips. Within the GPU, what you see is this: instead of one processor, you see lots of processors. That's important, isn't it? Or instead of 4 processors, in this example, we kept in CPU 4 processors, isn't it? Instead of 4 processors, each of these is a processor. You have lots of processors. I am writing P1, P2, P3, P4, so on Pn. All these are processors, isn't it? In a typical processor today, in the case of CPU, in the typical processor today, that is in the case of CPU, you see 4 core, isn't it? Or there may be 8 core or 6 core. Typically there are also single core boxes, isn't it? Yes, you may have single core, 4 core, 6 core, 8 core in the context of central processing unit, isn't it? But in the case of GPU, very common to see hundreds of cores, isn't it? You can see hundreds of cores in the case of GPU. GPUs where you can get 1024 cores, just say 1024 cores, or even 2048 cores, isn't it? That's the capacity. That is the beauty of GPUs. So each of these are cores. I'm saying P1 is a core, P2 is a core. So you have here lots of small processors, isn't it? In the case of GPU, you have lots of small processors. Each GPU core is much slower than, if you compare each GPU core is much slower than a CPU core, isn't it? See, your CPU core typically operate in 2 gigahertz frequency. You can think of it as a speed, while GPU typically operates few hundreds of megahertz, or maybe 400 megahertz, not even at gigahertz. That's important. Yes. Even it's not in the case of GPU, it is in terms of megahertz, not in gigahertz speed. Your CPU typically operate at 2 gigahertz, and 1 gigahertz equal to, what is this? 1024 megahertz, isn't it? So your GPU cores are much slower, but there are many of them. That's important. Your GPU cores are much slower, but there are many of them, and in each core, let me take this one block. Let me consider one core. Just I'm considering one block or one core. I'm just expanding on single block. This single block has 2 things. It has just see, it has processor, it has one core, it has cache. Just see, you have a core as well as cache in each. I'm expanding one block. In a block you can have one core and one cache. It has 2 things, isn't it? So the structure internally, this is the structure internally. It's like one core and one cache. Here, if you notice in CPU, what happens? One cache, just see here in the context of CPU, in the context of central processing unit, you have one cache that all the processors are sharing. isn't it? All the processors are sharing one cache. That's important. Just try to understand the difference, isn't it? On the other hand, what you have is in the case of GPU, this is called, you have in each block you have one core, one cache. This is called distributed storage, isn't it? Distributed cache. So literally what you have in each of these units is you have a core and cache. In the context of GPU, you have in each of these units, in each of these boxes is you have a core and a cache. I will show cache with the dashed lines. Let me represent cache with the dashed lines here. So if you look at this, you have processing unit here, isn't it? And you have memory cache here, isn't it? If you take any cell, if you take any box in the case of GPU, you have processor unit, here, and you have cache. That's important. You have processing unit or processor unit and cache, each box or each cell. So what you have here is distributed cache. That is important. And sum of all these cache, isn't it? In the context of GPU, you have cache, and sum of all these cache, the sum of all the distributed caches is, what is the sum of all distributed caches is called VRAM. That is video RAM, isn't it? So you might have heard GPUs. This GPU has 2048 GPUs has 2048 cores, and it has something like you might have heard that GPU has 2048 cores and it has VRAM of 8 GB, isn't it? What they mean, when they say VRAM of 8 GB is basically, if we sum up the storage that is there in all these caches across these thousands of cores, the sum up of all these, all of them, the sum of all of them is 8 GB. Since this data is very, very close to computational unit, just see in each cell your data is very, very close to computational unit. Just observe in the GPU, there are so many cells. In each cell you have a cache, a processing unit. In cache you have data. This data is very, very close to processing computational unit. It can perform the operations on the data very, very fast. This core can operate, every core can operate on corresponding data. If you observe in each cell, there is a core as well as data. This core can operate, that core can operate on the data available in that particular in that corresponding cache, data which is available in the cache corresponding to core, isn't it? Very, very fast. And the way it operates is, whatever data GPU operates on, first it will get it from RAM, isn't it? It will first get the data from the RAM, distribute the data across all the cores in the best, it will distribute the data across all the cores in the best or optimal way, and you can mention it in the code, in the program, on how to distribute this data. That's important. If you write low-level GPU code, there is something called CUDA, C-U-D-A, CUDA. CUDA is the programming environment or toolbox, you can think of it, to actually program NVIDIA GPU. And by the way, NVIDIA is one of the largest makers of GPU cards. NVIDIA is one of the largest makers of GPU cards in the world today. CUDA is a programming interface which defines through which you can say this is the data that I have in RAM. This is the data that I have in RAM. Which parts of the data should I bring? Which parts of the data should I bring into each of these cores? How should I build my distributed cache? So the way it works. So the way it works, some data is there in the RAM. Of course, you have your TensorFlow and Keras. Your TensorFlow and Keras use CUDA internally. But what's happening here is, if I have some data in the RAM, I can define how this data should split. Across the distributed cache. Any operation that I give can now run on the core can run here. This core 1, what is the core 1 can operate. See, core 1 can operate the data which is available in corresponding cache. In core 2, I have different cores in GPU, isn't it? There are n number of cores. Each core can operate data corresponding to its cache, isn't it? Just try to understand this particular diagram, isn't it? They have thousands of cores as example to maintain process which has only just if you recall CPU. In the case of CPU, you have only 4 cores, isn't it? It do lot of parallel operations. So in a GPU, in the case of GPU, AB, how can I multiply it? AB will works like A1 into B, A2 into B, A3 into B, A4 into B, A1000 into B, all happening in simultaneously. A1001B, A1002B, so A2000B happens in the second time stamp, isn't it? So here, but in the case of CPU, just try to recall, in the case of CPU, you have 4 parallel tasks. If one of the 4 parallel tasks over, if after completing these 4 parallel tasks, next 4 parallel tasks will start. That's the case of CPU. In the case of GPU, what's happening in the case of GPU? In the case of GPU, 1000 parallel tasks are running at one instance. Once these are over, then we will start the next set of parallel tasks. And to do all of it, remember, everything is being multiplied by B. Just see, so what I do in my distributed cache, suppose, just see, everything is multiplied by B. Suppose this is my GPU. Let's assume this is my GPU and I have cache here. So what I will do here is, in first iteration, I have thousands of these. In first iteration, what will do here is, in this computational unit, I will start A1B. I will keep in first box, and it in second one I will store A2B. In third cell, I can keep A3B, so on, A4B, A5B, still I can say A8B. In each cell I can keep A and B, isn't it? Some portion. So I am distributing my A and B carefully, so as to enable this, the matrix A, to calculate matrix A into B very, very effectively. And this is very possible because I have lots of cores. I have smart way to distribute data. That's important. I have smart way to distribute data. Remember, even your A1B is basically on operating like this. What is A1B? What is the meaning? In first cell we are keeping A1B, in second cell we are keeping A2B, in third cell we are keeping A3B, in so on so forth. What is the meaning of A1 into B in first cell? First cell means you have cache as well as core, isn't it? This is your just see, I have just see, this is this core multiplies A1 and B. First core multiplies A1 and B, second core multiplies A2 and B, third core multiplies A3 and B. What is the meaning of A1 and B? This is your A1 and you have B. Even this operation requires some multiplication, some additions that will be performed by this core, isn't it? And because I have thousands and thousands of cores, GPU tends to be much faster. That is important. Because I have thousands and thousands of cores, GPU tends to be much faster if you have parallelizable tasks. That's important. It is much faster for parallelizable tasks. So this is the crux thing. GPUs are fast if you have parallelizable tasks. Remember, multiplying a matrix with a vector is highly parallelizable task. That is important. My capital A multiplied by B does not depend on my capital A1 multiplied by B, does not depend on A2 multiplied B, and does not depend on A3 multiplied by B. Yes, multiplication of A1 and B is independent of multiplication of A2 and B, and it is independent of multiplication of A3 and B. All these can be performed by different computational units, because matrix operations, remember what is all of the deep learning. If you think about it, deep learning literally, I can say deep learning literally has lot of matrix multiplications and additions. It's all basically bunch of matrix or vectors. You can think of it as matrix multiplications or vector multiplications and additions, or you can think of it as broadly as tensor operations, isn't it? That's deep learning. That's what deep learning says. That is deep learning. It's basically tensor operations. You are basically doing a bunch of matrix or vector multiplications and additions. That's what it is. Look at an update. What is my update equation? WT weighted t equal to weighted t minus 1 minus eta into derivative of L with respect to weight vector. Now instead of one weight, if any w here is a vector of all the weights, that's why I'm keeping a box. W is a vector of weights, set of weights. I can write my updated equation the form of vector represent. How can I write? Wt equal to Wt minus 1 eta into del L with respect to W, isn't it? So this is vector operation. What is Wt? Wt is a vector, Wt minus 1 is a vector, dou L with respect to W. All of them are vectors. Basically all these are vectors. Instead of doing operations on single weight, vector means you have multiple weights, isn't it? I can perform operations on the whole vector of weights, isn't it? Matrix of weights, vector of weights, matrix of weights. And what is this? This is all these are vectors, isn't it? You can think as addition with this I can treat as Wt minus 1 minus eta into dou L with respect to W. I can treat it as addition with minus sign, isn't it? So lot of deep learning stuff is literally matrix multiplication and matrix additions. Are to be precise, it is tensor operations, basic operations like multiplication and addition on tensors, and these these are tensor operations. These tensor addition and multiplications are highly parallelizable. That's important. These tensor additions and multiplications are highly parallelizable. You have seen example of A1 into B. Just see, you have seen example of A1 into B, A2 into B, A3 into B. All these are parallelizable. Similarly, adding two matrices, just A1 into B is A1 into B, A2 into B, A3 B. All these parallelizable tasks. Similarly, matrix addition, first row with the first row. How can I add two matrices? First row of the first matrix must be added with first row of second matrix, and second row of first matrix must be added with the second row of second matrix. These are independent tasks. Addition of two rows. Similarly, adding two matrices can also be done parallelly. This addition with this addition has got nothing. First addition has got nothing to do with the second addition, isn't it? Because lot of the tasks that we have in deep learning are highly parallelizable tasks, and since GPUs are thousands of course, and very efficient. GPUs have very efficient distributed cache. GPUs tends to run in reality. When actually run deep learning algorithms, all GPUs, they tend to be 10 to 100 times faster. That's important. All the GPUs are tends to 100 times faster than they tend to be really faster. And those of you wonder which part you need to buy, which one you need to buy GPU now to do deep learning. If you have financial resources, these are some of the most popular GPUs: GTX 1080, GTX 1080, GTX 1070, GTX 1060, GTX 1050. So I think GTX 1080 has 11 GB of VRAM, if I am not wrong. Just check this one. This has and GTX 1080, this has 8 GB of VRAM. The more VRAM, that's simple. The more VRAM, this point important, the more VRAM you have, the more parameter parameters you can have in your deep learning model, isn't it? More parameters you can have in your deep learning model means you can that is complex model. So in a nutshell, if I have more VRAM basically implies build more complex models with more weights, because all of your weights which you are stored in visual RAM, it is also called video RAM. Video RAM is nothing but distributed cache. It is nothing but sum of all the distributed cache that you have in GPU. So the more the RAM you have, the more the VRAM you have, more complex models, more weights can be trained, more complex models can be trained, the more VRAM, isn't it? These are the some of more popular. Just go to amazon.com and amazon.in also. Just check the price of your GPU is not cheap, that's important. But if you have the financial resources, it's a good investment to buy. If you are planning to do deep learning for next 3 to 4 years, for those of you for whom the financial resources are tight, are difficult to have constraints on financial resources, are those of you think of, I don't want to buy right away, I want to experiment with it. In next video we will show you an online, this is important, and in next video we will show you an online tool called Google Collaboration. It's called Google Colab, which is an online tool that's that provided by Google Research for education and research purposes, where you can run your high-end complex deep learning models on Google Cloud. You can run, which has both where you can have in Google Cloud you can have GPUs and CPUs. I will show you how to use Google Colab in next video. By the way, you can do deep learning on CPUs also. It takes more time. That's it, isn't it? Just go through this lecture. If you have any difficulty, please keep a comment. Thank you very much.